What's up, Team Ropke here? 2J, inverses of functions. Let's kick things off with some vocab that might be new to you. A one-to-one function is a special type of function. It has a two-part definition. First part just says that it's a function. Every x has exactly one y. Second part is the converse of that. Every y has exactly one x. And if a function is one-to-one, it will have an inverse, and that's going to be our notation for inverse. I think you've seen it before, but if you haven't, that -1 is not an exponent. It will never be an exponent unless it is on a variable or a number. You've almost definitely seen inverse sine or arc sine. Same idea here, okay? That's going to be the inverse of f of x. Confusingly, perhaps, when I write that, that does mean sine squared, but the -1 is never an exponent. It's always going to be the inverse. Anyway, what do we need to know about inverses? We got its notation. Since it is, in fact, a function, it's got to satisfy the vertical line test. That should be obvious. The inverse function will be the reflection of the original function over the line y equals x. We'll see some examples of that soon. And also, when we compose the inverse with the original in either order, we always just get x out. And that should make sense, right? We're doing a function, and then we're doing the opposite of that function. So they should undo each other, and we should just get x out in the end. This is the only time when the composition of functions done in any order will always give you the same answer. Last point, the domain of the inverse is equal to the range of the original function, and the range of the inverse is the domain of the original function. Basically, this means we're taking y's and x's and we're switching them. And that's going to be the way that we're going to algebraically work out what the inverse function looks like, is just by switching x's and y's. So here's an example of something that is not an inverse function, y equals x squared. Right? It's not an inverse function because it's not one-to-one. We can see here that most of the y values actually have two x values associated with them. So that could not be a function. By the way, this is called the horizontal line test. A vertical line test tells me if a relation is a function. A horizontal line test tells me if an inverse function might exist or not. So here clearly, because it does not pass the horizontal line test, this does not have an inverse. I could make it have an inverse if we do something called restricting the domain. So if we just ignore a whole lot of the x values, then whatever's left will have an inverse. You will see this certainly with trigonometry, the inverse sine, cosine, and tangent functions, they all have restricted domains. Obviously, if you visualize a sine, cosine, or tangent curve, they certainly do not pass the horizontal line test. So when we talk about their inverse functions, we have to restrict their domains. But more about that in many, many chapters from now. Part C, find f inverse of x. So the idea is we're going to start off with the original function. We're going to switch x and y. We're just going to rewrite the original function with x's and y's switching places. And then we're going to solve for y. So in this case, we're going to take the square root of both sides, which would be y is equal to plus or minus the square root of x. But we ignore the minus because we know that y had to be greater than or equal to 0, since in the original, x was greater than or equal to 0. So we have y equals the square root of x as the inverse. But we're not going to write it like this. We're always going to write it in this form. If we're talking about an inverse, we want to call it an inverse. You will lose marks in most situations if you write the equation of an inverse function as y equals. So please don't do that. And finally, letter D, here we have a sketch of both the original function as well as its inverse. And you can see that they are reflected over the line y equals x.
So I want to share with you kind of a silly trick to help you graph inverse functions while you're still getting used to the process. And it relies on the fact that when we go from a function to its inverse, we have to switch x and y. But more specifically, we need to switch positive x with positive y and negative x with negative y. I'll show you what I mean with this piece of cellophane. Now you'll notice that my axes are labeled as positive x, positive y, and negative y. And I have our friend, the function y equals x squared, as long as x is greater than or equal to 0. I want to graph its inverse. Now I want to switch the positive x and y axes. And I can't do that, for example, just by rotating this way. I've got positive x is pointing up now, that's great, but positive y is pointing to the left. That's no good. Likewise, I can't just rotate this direction. Now y is going in the right direction, but x is flipped around. And neither of those look like what the inverse of x squared should look like. You might also notice that the line y equals x has been rotated in both of these, and that's no good either. What I can do, however, is flip it vertically and then rotate it. And now you'll see that I've got x plus pointing up and y plus pointing right. And that's also exactly what the inverse function should look like. That looks just like y equals the square root of x. Now the best part is you don't need to do this on cellophane. You can actually do this on paper during class, even during an exam, as long as no one's cheating off of you. If you've got your function drawn on a piece of paper, all you need to do is flip it and rotate it, and then hold it up to the light. In fact, you can probably see it already through this paper, but just in case you can't, so there's no excuse for you to not be able to visualize an inverse function based on the original. And eventually you'll be able to do all this just in your mind, but if you're uncomfortable with the process for now, this is a trick you can use to help get you there.
Okay, this problem is going to give me an opportunity to show you a little shortcut that we can use. For letter A, we want to find what is g inverse of -1. So I think the natural thing to do here is to work out what g inverse is and then input -1. So let's do that. G inverse, we're going to have x is equal to 8 minus y over 2. So that means 2x is 8 minus y, which means y is equal to 8 minus 2x. Inputting -1 into that, we get 8 plus 2, which is 10. Okay, so g inverse of -1 should be 10. But there's another way to figure this out. Remember that for an inverse, the x's and y's will be switched from the original. So if I'm inputting a -1 as an x value into the input, that means that that -1 should have been a y value for the output. And if I just solve this, I'll get 10 as well. And if I just solve this, I'll get 10 as well. And that's definitely the same. And if I just solve this equation, I'll get 10 as well, and that's going to be the answer. So I can try letter B in the same way. I could work out what F inverse and G inverse are, and then substitute -3 and 6 into them to show that it's equal to 0. But I think it's probably just easier to say, well, if this -3 is an x value for F, that means it should be a y value for so again, if this -3 is an x value for F inverse, that means that it should be a y value for F. So that's 2x is -8, x is -4. And if 6 is an x value for G inverse, it'll be a y value for G. So that would be 8x is 12. -4 is equal to x. And then clearly, if I take -4 minus -4, I get 0. So that's going to be true. And finally, letter C, f of G inverse of x is equal to 9. I guess we could think about this a few different ways. We could say that since I know f of something is equal to 9, we can just put G inverse into f and solve this. That's going to tell me that G inverse of X has to be equal to 2. And then I want to know if 2 is the Y value of G inverse, that means that it's going to be the X value for G. So that'll be 8 minus 2 over 2, which will be 3. For another answer, we could have worked out what G inverse is, which I did earlier. G inverse was 8 minus 2x. So that means that f of G inverse will be 2 times 8 minus 2x. Plus 5 is 9. And then I just solved this equation. And that's going to get you x equals 3 as well. So different options again. I'm not sure which is necessarily faster, but there you have it. Okay, so this is a fun one. We're given a particular f and g, and we want to show that f inverse of g inverse of x is equal to g of f all inverse. Now that's quite a mouthful, but it's doable. It's doable. First thing I would do is I'd work out what f inverse and g inverse were, and using the same process as in the previous examples, we can see that f inverse is equal to x over 2, and g inverse is equal to x plus 3 over 4. And you know, just a quick aside about how you can kind of mentally check to see whether your inverse function makes sense or not. Just look to see whether it is actually the opposite of the original one. Here we have x divided by 2, and here we have x times 2. Those are clearly going to be inverses. Here, this one's a little trickier. We have, first it's a plus 3 compared to a minus 3, and then we're dividing by 4 instead of multiplying by 4. Not only are those operations switched, but also the order of those operations are switched. In the original, we had to multiply first before doing addition or subtraction. In the inverse, we actually have to do the addition or subtraction first before the multiplication or division. And that's generally going to be the case. Just something to keep in mind if you want to mentally check whether you've made an error or not. So what is f inverse of g inverse of x? That's going to be x plus 3 over 4 all over 2, or x plus 3 over 8. And on the right, we're going to do g of f first of all. So g of f is going to be 4 times 2x minus 3. I'm going to need to invert that in a second. Let's just simplify that. That'll be 8x minus 3. So now I need to work out the inverse of 8x minus 3. Again, just imagine that's y equals and use the process that we saw in the previous examples. But also if we kind of think about what we just said about that one and how the numbers are going to switch around, yeah, the inverse here is going to be x plus 3 divided by 8. I can see that without having to actually do the work. So there are shortcuts that you can use for simple ones, although, to be honest with you, if it was on an exam, I would show the work. Anyway, we can see here that the two are equal. So yeah, in this case, this is equal to that. And, you know, again, I was wondering to myself, is this going to be true all the time? And yeah, it is. You can actually look, and plenty of websites and textbooks are going to have this particular definition in there someplace. The proof is actually pretty complicated, so I'm not going to walk you through that. I will say this, however. If I put on my socks and then I put on my shoes and I want to undo all of that, get back to my bare feet, I've got to take off my shoes and then take off my socks. Hopefully this silly example gives you an intuitive sense of why this happens to be true. If you're really interested in looking up a formal proof of this, you can give it a shot, but I'm definitely not including it here. Anyhow, that's inverses. Hope you enjoyed.